Okay, so we finished last hour talking about the assumption in the black oil PVT model that the surface oil from the gas phase and the surface oil from the oil phase are assumed to be equivalent. In reality, the model is assuming that you can add surface oil from an oil phase and surface oil from a gas phase together, 1 cubic meter of each, and you get 2 cubic meters. That's correct. Okay, it doesn't matter what color they are. It's like diesel and gasoline. That's correct. But you don't get a mass balance out of that, because if the densities and or molecular weights are different, then you're going to start having a mass balance error. Okay, and that's in reality what we live with. But so we have a volume balance in our reservoir simulation models. For example, we try to drive that to 0 or some epsilon, but even with this going to 0, you still get a mass balance error. But basically, these models don't consider or worry about it, mass disappearing. And for the most part, you can say that's okay. But there's still a problem in that the fact that this is not equal to this and this is not equal to this. This causes a problem, a different kind of problem. This affects the calculation accuracy of phase densities. Okay, in these models, be it the tubing model or the reservoir model, if you have gravity moving gas and oil phases up and down, then getting the wrong phase density can be important. Okay? Well, so the question is how we get these phase densities. So we're going to come back to this once we finish talking about the second type of volume fraction. But let's just put a note in this that we're gonna end up with phase density errors that will cause potential problems in our modeling. Okay, so we covered the first kind of black oil property is the solution. This is called the solution gas oil ratio, capital RS, and this is called the solution oil gas ratio, little rs. And why do we call it solution? Because the solution GOR is the amount of solution gas in solution in the oil phase. So like this air has a certain amount of water in solution in the air. Well, that would be like the little rs. It's the solution oil in the gas phase. Okay? It's the solution oil in the gas phase. So that's like the air is the gas phase, and it's like the water component is like our surface oil. If we take the bottle here of water, okay, the amount of air in solution in the water, okay, now that I've shaken it up, it's an equilibrium system. So now the water has a certain amount of air dissolved in the water. It's not really correct because if you look at the components in the water phase, in the liquid phase, the oil phase, if you look at the nitrogen, oxygen, CO2, CO content in the water, that distribution is definitely not the same as the distribution of those components in the air itself, because CO2 likes water better than nitrogen. Okay, but we just talk about air as a pseudo component. So the air, quote unquote air, dissolved in the water here is equivalent to the RS term, the solution gas component dissolved in the oil phase. And we say the solution oil gas ratio is the solution oil, the water component dissolved into the gas phase in this bottle, because the air in this bottle is now saturated with H2O, not like the air in the room here. You can be happy it's not saturated in the room here, because we'd be sweating, right? I think, or something. You'd be so this is the first two terms, and effectively these are compositional description of the two phases. And now we've got the second volume ratio, and this is the volume ratio referred to as the volume factor. And historically, the volume factor was associated with reservoir calculations. Okay? Now it's used in production tubing and pipelines all over the place. The formation volume, the volume factor is used everywhere. Okay? But historically, it was called the formation volume factor, because it was down in the formation, in the reservoir. So I'm going to put this in parentheses, formation, because even though that implies that it's at reservoir conditions, we still use these volume factors in production tubing, in pipelines, far away from the formation. But historically, we call this FVF, formation volume factor. And the term, the symbol is capital B. Capital B. And once again, there's a volume factor for the gas phase, and there's a volume factor for the oil phase. Okay? But the generic volume factor definition is that the volume for a particular phase, it's the volume of that phase at some pressure and temperature that we started with. Remember, we talked about we have this composition in pressure and temperature. It's outside the phase envelope, and it's got a volume. And if we take that volume and divide it by the surface volume of that gas, okay, now it's a component, but okay, coming from that phase. So we've got two of them. We've got the oil volume factor, which is the oil volume at pressure and temperature, divided by the surface oil volume, that's a component, from the oil phase. This is called the oil formation volume factor. This is a very important number to remember, because oil is an important money generator. Okay, so even idiot geologists, not all geologists are idiots, I'm just saying those who are, even they know about the magnitude of the formation volume, the oil formation volume factor. Okay, it's an important number, and it's typically ranging from 1.0x, which is about as small as it gets, for Venezuelan, Canadian heavy oils, okay, to as much as, very seldom larger than this, as much as around 3. Okay? And typically, I'm going to say it's ranging in today's oil reservoirs, typically somewhere between 1.2 and 2 for most oil fields. Okay? Now, what does it really represent? It's easier to think of it upside down. Okay? It's easier to think of it upside down. Because upside down, and we sometimes use that, it would be the inverse oil volume factor. We actually use that. It's little b is just defined as 1 over BO, little bo, okay? And that represents the volume of surface oil coming from the oil phase divided by the oil phase at pressure and temperature. And this form of the volume factor, it's not as common to use it, but this is saying that if we start with 1 cubic meter of this oil phase at pressure and temperature, 1 cubic meter, and the big BO is, the value of it is 2. Okay? It's saying that my 1 cubic meter of oil phase turns into a half a cubic meter of sellable oil. So it shrinks 50%. Okay? So it represents a kind of shrinkage factor. Okay? So this is what we refer to usually as a shrinkage term. The actual shrinkage factor would be 100%. The actual, if you want to talk in terms of a shrinkage factor, and sometimes that's important, that would actually be 100% times, it would be, let's see, 20, 30%, I have to be careful here, 1 over 1. Let's see, if it's equal to, let's say it's equal to 2. If BO is equal to 2, let's just make sure this is right. If that's 2, then little BO is a half, and the shrinkage factor would be 50%, right? So the oil shrinks by 50%. If BO is 1.5, then little BO is 2/3, right? 60, okay, 2/3, and the shrinkage factor would be 33% with this equation, right? It shrinks by 33%. Well, that's correct. Yeah? And in the other extremities, you've got, if it goes as high as 3, then the little BO is 1/3, and the shrinkage factor would be equal to, and this is about as big as it gets. You start with 1 cubic meter, and it shrinks by 67% down to 0.33 meters. That's a hell of a lot of shrinkage. But typically, the shrinkage is less than a half, less than 50%. And if you've got BO of 1.1, then little BO is 0.99 or 0.9 approximately, and you have a shrinkage factor of 10%. Okay, about, yeah.
Should it be 1 over BO minus 1?
Probably. There we go. I'm just seeing if you guys are awake. Is that right? Or not? Is that right? I'm not awake, so I think that's right. Okay. So this is the oil formation volume. It's a very important number, okay? Because the geologist will figure out we've got umpteen million barrels of reservoir oil volume. And of course the president of the company wants to know how many sellable oil volumes is that. And that's when they come ask the reservoir engineer. Or the geologist tries to steal the number from the reservoir engineer. So the geologist can tell the president of the company, so the geologist gets the raise. Okay? So be careful. Don't give any numbers to the geologist. They might trick you. Okay, so then we've got the gas formation volume factor. And here we have to be a little bit careful. That's called BG, as in the company, kind of. And BG is just defined as the volume of gas at pressure and temperature, gas phase, divided by how much surface gas we will get from that gas phase. That's standard conditions. And this is also a very common term for people working in gas engineering. You also have this, and that's quite a bit used. That would just be surface gas volume coming from the gas phase divided by the gas phase volume. And what this little BG term is telling you, if you have a cubic meter of gas phase at reservoir conditions, you bring it to the surface, and let's say you get no oil, no surface oil, it's a dry gas. Then this term would give you the expansion. You turn it into 200 standard cubic meters of sellable gas, or 100, or 350. Okay, so this is the gas expansion factor. It's typically between 100 and 250. Okay, that's how much gas expands from typical reservoir conditions to surface conditions. Yeah? Huh? I can't hear you.
Is it constant?
No. That's at one. It's definitely a function of pressure. Yeah. Yeah. It's definitely a function of this pressure. Very much so a function. It will change over time if the pressure changes over time. That's right. But if you just look at an initial gas reservoir anywhere in the world, it'll typically have this expansion factor somewhere between 100 and 250. Could be a little less, a little more. But with this formal definition, 99% of textbooks assume little rs is equal to 0. Even today's textbooks. And therefore, they give an equation for BG that we've looked at before based on that assumption that looks like this. And I'll just, to remind you, Z factor is a function of pressure and temperature. Okay? So this is what you'll find in 99% of the textbooks. But in most gas reservoirs today that actually produce some of this nice surface oil from gas, condensate we call it, okay? We make a lot more money on that. This equation is not right because this assumes that this is equal to this. another way of putting that is that this is equal to 0. But, in fact, for gas condensate reservoirs, Ng from the gas over Ng can range anywhere from 0.85 to 0.99. Okay? I'm sorry, that's not written correctly. This should be of the total gas, of the gas phase. Which means that of the total gas phase, what becomes oil is in the range from 15% to 1% for gas condensates. But even with 1% turning into a condensate gives you a lot more money. Okay? Because you get so much more money per mole sold as a liquid. And this equation is going to be off. It's going to be wrong for these gas condensates by this amount. So this is, if this value is 0.1, then your BG from this equation is wrong by 10%. Okay? Because the true BG, which is what we refer to in the book as BGD. Okay, this is the true. It's called BGD. I'll tell you why later. Which is exactly this. Taking into account that we lose some of the moles as a liquid. That equation for that is the same as what we have above. Times 1. I have to be a little careful. doing it in my head. You see, you're going to end up with less than what you have. So this number is going to be bigger. So we need this to be like this. That's what it should be. Where this number here is somewhere between 0.01 and 0.15. And by the way, this number here can be approximated as, if you have gas compositional analysis, if you take what is about C6 plus, all of the components C6 plus, or maybe C5 plus, if you take the mole fraction of what is C5 and heavier or C6 and heavier, okay, whatever that number is, that is a very good approximation of this ratio. So you can estimate the error in using the standard textbook equation by simply knowing how much of this heavy stuff do I have in my gas. And that will be approximately give you the error, and it'll give you a way to correct that textbook gas formation volume factor equation. Okay. And in the book, chapter 7, because we differentiate, instead of leaving BG to be, oh, what is it we're talking about, Curtis, we actually, the textbook BG, we call BGW. Okay? BGW. And we call this true BG, that you actually, according to this definition, BG dry. Okay? What does it mean by dry and wet? The dry, D for dry, means that the surface gas is dried from the is dried by removing the surface oil. OG. Opera ghost. Okay? You take the OG out, removing the surface gas from the surface gas. Okay? Means we've dried the surface gas. We're taking the condensate oil away. W stands for wet, and it means that we assume all of the surface gas is equal to the reservoir gas. Okay? All of the surface gas equal to the reservoir gas. Okay? And that surface gas volume is wet because we still have the condensate there. Okay? It's a wet surface gas. Okay? So it's a wet surface gas because it still contains what is actually going to become this valuable condensate liquid. But if you use that equation, you're saying that I get no condensate liquid, I only get surface gas. So it's a very pessimistic way to do your engineering. It's a way to get you a job demotion instead of a job promotion. And the first field in Norway, Ekofisk, that was developed because their reservoir simulation models made this assumption that gas did not yield condensate. Okay? The recovery factors, which by just depleting the 6 billion barrels, were only about 13 recovery percent. And when they included the fact that when gas did come out of solution from the oil, it would bring with it condensate. When that gas produced to the surface, it would yield the condensate. The recovery factors went up to about 17.5%. It was a big effect on the depletion recovery performance. It's a lot of money. It's a lot of engineering salaries, to put it that way. 3.5–4% of 6 billion barrels. Just kind of ignored because of this bad assumption. So you need to be careful. This is the equation you'll always see. This total equation this term here is what you want to use in your engineering. Okay. Okay. And then the final thing I want to mention about the Blackwell PVT is how to calculate oil phase and gas phase densities. Okay? Because the Blackwell PVT table consists of BO, RS, BG, D, and little rs, 4 quantities. Okay? So we know RS, BO, little rs, BG, D, okay, at some particular pressure and temperature. And we want to, and we don't know what is the density of the oil phase and the density of the gas phase. That's what we want to know. And that's density at pressure and temperature. Okay? And we need this for engineering calculations involving transport or hydrodynamics influenced by gravity. Okay? That's why we need densities. Static column in the production tubing, down in the reservoir, where's the gas oil contact, and so forth and so on. Gravity segregation. When you flow, gas will tend to flow above the oil, and oil will go below. Water likewise. So we need the gas and oil densities at pressure and temperature. And for the Blackwell PVT model, you have 2 equations. You have the gas equation is equal to the surface gas density plus the surface oil density times the solution oil gas ratio divided by BG, which is a function of pressure and temperature, as is little rs. The oil density equation is surface oil density plus surface gas density times solution gas oil ratio. That's a function of pressure and temperature divided by oil formation volume factor at pressure and temperature. So these are the 2 equations. And what you see is that these are the typical PVT, Blackwell PVT properties you hear about or see in tables. Okay? And they're functions of pressure and temperature. But to calculate oil density, you need 2 more numbers. Surface gas density and surface oil density. And these are 2 constants. Physically, they're not constant. Physically, they're different. The surface oil from the reservoir oil is different than the surface oil from the gas. And they vary as a function of pressure. So in reality, but in the Blackwell PVT formulation, they're considered 2 constants, 2 numbers. Even though in reality, this is a function of pressure and temperature. It's not equal to the surface gas from the oil, which is also a function of pressure and temperature. And likewise, the surface oil density varies with pressure and temperature, and it's different for each phase. So even though these things are all changing, we just simply say ignore it. Okay? We're only going to use two numbers. Okay? That is a fundamental part of the black oil PVT formulation. And they're used in these two equations here. Now, next Tuesday, we will talk about how these four properties, BORS, BGD, and little rs, vary as a function of pressure for a given temperature. Okay? We're going to talk about that. Second, we're going to talk about how the hell do we get these numbers? How do we create these tables? Third, I'm going to show you some National Football League videos, maybe. I don't know. Okay. All right. I will, God willing, and give you problem 2 during the weekend to do flash calculations, saturation pressure calculations, like we did in class on Tuesday. Okay? Any questions? So, if you want to know what reading material, chapter 7. Okay? But part of that's talked about today, part of it will be talked about on Tuesday, and then, okay.